let's talk about two definitions. So the first one is the definition of a partition of a set S. And a partition is a collection of subsets. So a collection of subsets called SI, such that, well, the union of all of the SI is going to be S, right? So this big U is my union, and SI and the SI are disjoint. So that means that SI intersect SJ are disjoint, or excuse me, SI intersect SJ is the empty set for I not equal to J. So that's the same thing as saying the SI are disjoint. So the example of this is you can have a partition which, you take your finite set. So let me draw a finite set. So this, circle blob thing will be my set, and I'll draw some blue dots for elements. So one partition of my set could be like this subset, this subset, this subset, and this subset. So this is maybe S1, S2, S3, and S4. So here's another example. So let's take the set 1, 2, 3, and 4. So a partition of this set would be, so partition would be, here's one partition, 1, 2, 3, and 4. Right, so you have to have all of the elements in the set are in one of the sets of the partition, and you can't have any overlap between any of the sets of the partition. Okay, so that's one definition. Here's another definition. The definition is an equivalence relation. So an equivalence relation is, well, we're given a set, so it's an equivalence relation on a set. So so I guess we write it in a certain way. So the way we write it is sort of as an operation. So A equivalent to B. So we would write it is, so I guess it would be I'll call it a relation. What's a good formal way of writing this? I think, yeah, I guess we'll call it a relation between sets. So a relation between the elements, A equivalent to B between elements. So somehow you can say this, you can think of this as some sort of, Boolean function. So the idea is for every element A and B, either A is equivalent to B, in which case we write A is equivalent to B like this, or we would say A is not equivalent to B. But I don't want to talk about like Boolean functions or anything. So we'll just call it a relation between elements, such that, so the following is going to hold. We need to be reflexive, So A is going to be equivalent to A. We need to be symmetric, which means that A equivalent to B is the same thing as B being equivalent to A. And lastly, we need to be transitive. So that means if A is equivalent to B and B is equivalent to C, that means that A is equivalent to C. Okay. And so, examples of equivalence relations are the first and best example is equals. Equals sign is a relation, an equivalence relation. And in particular, the equals sign is kind of the thing that equivalence relations are modeled after. These are sort of the things you really need to know about equality to make them equality. So let's say equality on a set. Another example of an equivalence relation might be, so if you take, you can take like the set of matrices, and you can talk about similarity. So like, say you have GL2R or something, and or GLNR, really, it's fine. And then say, the matrix, A, B, C, D, it can be GL2. A, B, C, D is equivalent to E, F, G, H if, if you can write an invertible matrix such that if I'll just say if the two matrices are similar. And you don't even need, I guess, really you don't want GL2 here. You want the space of all possible matrices, M2 of R is what you want, because you don't need invertibility to talk about whether two matrices are similar. So that's an example for people who have seen linear algebra. If you haven't seen linear algebra, don't worry about that so much. So now comes the sort of important part, which is that I have this theorem, which is that every partition of a set, let's say a set S, gives an equivalence relation. And vice versa. So every equivalence relation gives a partition set. So let's do a quick proof here. So how is this going to work? So given a partition, that's S is equal to the union of Si, or one thing I could write, so here's a mathematical notation. If I write it like this, with sort of square ends of the U here, this is called disjoint union. And so a disjoint union, has in the definition that each of these Si are going to be disjoint. So if I have a disjoint union like this, I can say that A is equivalent to B if and only if A, so A and B are in the same SI, right? So what we have is, right, so what we know is that A is in SI for exactly one I. And then B is in another one, and then B would be in SJ, so that it might be different. The one that B is in might be different likewise. And then we say A equivalent to B if I equals J. So that's how that one works. And then the exercise for you is to verify this is an equivalence relation. So that would be, verify reflexivity. That shouldn't be too bad. Verify symmetricness and transitivity. So, how that would look in this set, right, is like 1 would be equivalent to 2, but 1 would not be equivalent to 3, and 1 would not be equivalent to 4, if we were using the example of this partition right there. Okay, so now the other half of a proof, So the other half of the proof will go given an equivalence relation. Equivalence relation. So now we have the tilde. We have the equivalence relation. So we need to construct a partition. So let's call it S sub A, and I'm going to define this as so one quick note on notation, when you have these colon equal sign, generally that means you're defining whatever's here next to the colon. So SA is going to be defined as the set of B in S such that A is equivalent to B. So that would be SA. And then what we need to show is, well, okay, we need to show that these SA will be a partition. And in particular, what we can show is that if A is equivalent to B, so this is a lemma, or it can also be an exercise. So the lemma that I'll ask you to prove is if A is equivalent to B, then SA equals SB. So you should try to prove this. You're going to want to use, you'll use the axioms of the equivalence relation to show it. And I'll give you a hint too. The hint is that this is symmetric, meaning that A might as well be B and B might as well be A. So you can interchange them. So you should prove that SA is contained in SB. And then that will get you the whole thing. Because SA will be contained in SB, but then because of symmetry, SB will be contained in SA, and then they'll both be contained in each other, so they've got to be equal. Okie doke. Now, finally, the last step is, so pick one element SA, or one element A, in each of the distinct SA, and then the union, and it'll be a disjoint union, these SA, that will be equal to S. That will finish up the proof.